You can see my screen now, isn't it? Let's start. The week 10 chapters are 8.3 sampling distribution. So we start with the 8.3 sampling distribution and we'll try how much we can complete. What is sampling and what is sampling distribution? Sample mean, sample median, sample range. We have seen all these things in the introductory chapter. Mean, median, range, mode are examples of statistic. They are called a sample statistic. So a sample statistic is just a measurement computed from a sample data. If you have 5 elements, you can add them and divide by 5, you'll get the average. You can write them ascending order, find the middle value, median. Range is the difference between maximum and minimum. Mode is the value of the data that occurs very frequently. A sample statistic is itself a random variable. So every sample statistic mean itself is a random variable. Median, range, mode, everything is a random variable. So as a random variable, it has its own probability distribution. When there is a random variable x, then there is a probability. The probability distribution of a sample statistic is called a sampling distribution. So if you find sample mean, sample variance s square, sample median, mode, they are called sample statistics. So when you find probability of them, you call it sampling distribution, right? And you know, if x bar is sample mean, mu is population mean. If s square is sample variance, sigma square is population variance. So they are called population parameters. These elements are called sample statistic. Go ahead. The sample mean is a random variable. The most important sampling distribution is that of x bar. Most often we will use the probability distribution of the mean. The sampling distribution of x bar is called the sampling distribution of the mean. Our goal is in the next section is to discuss the sampling distribution of sample mean, probability of x bar. Sampling distribution of means, central limit theorem. So here, if x bar, what is central limit theorem? There may be questions from central limit theorem. If x bar is the mean of a random variable of size n taken from a population with the mean mu, you understand anything? And with the finite variance sigma square, then the limiting form of the distribution of z. We already know the formula of z. What is it? Z is same. We have used x bar minus mu, x minus mu divided by sigma, isn't it? This x was replaced by now x bar because this was only probability of x, random variable x, isn't it? But here we are finding probability of x bar, the mean. So x will be replaced by x bar, sigma will be replaced by sigma over root n with the degrees of freedom. So the n is the sample size. So if x sigma is the sample, population parameter, population standard deviation, sigma over root n will be standard error or standard deviation of the mean. So we call it sigma x bar. Sigma x bar is sigma over root n. Actually, this formula should have been z is equal to x bar minus mu over sigma x bar. It's not a general sigma. Sigma divided root n. So sigma x bar is known as sigma over root n. And this formula gives us to convert the mean into z and then use the normal table again to find the probability. So this distribution, as n goes to infinity, the standard normal distribution, what they say is whatever the distribution of the x bar, whatever the distribution, isn't it? It can be following binomial or Poisson or any discrete or continuous distribution. When the sample size is higher, approaching infinity, very large. So when the sample size is larger, this can be the x bar can be approximated by using normal distribution. In other words, if n is large, generally greater than 30, then we may treat the random variable z above as if it has the if it has what is n of z comma 0 comma 1 normal. This is the notation for normal distribution where mean is 0 and standard deviation is 1. Variance is 1. Another important theorem 8.3. If independent samples of size n1 and n2 are drawn, now we are see in this previous case it was only one sample. Here you are taking two different samples. There is a population. This population is called just your sample space. You can call this population, isn't it? Two different samples are drawn of size n1 and another size n2. Assume that there are capital N number of elements in the sample. I mean the population. Call it population. Okay, we are drawing from two populations. This theory is actually this definition says you are taking two different samples, not from the same population, from two different populations, discrete or continuous, with the mean mu and mu1 and mu2, variances is given respectively. Then the sampling distribution of the difference of the means. Isn't it? This sampling is you have one population, call it population 1, another population 2. From here you take a small sample S1, here another sample S2. Isn't it? This population has mean mu1, where sigma 1 is standard deviation. This is for mu2 and sigma 2. Now we are finding the sampling distribution of the means. For the particular sample, the mean is x1 bar. For this particular sample, the mean is x2 bar. If these means are equal, it means that the population are equal. They are from the same population. If the means are not equal, they are from different population. So the sampling distribution of the difference of means is approximately normally distributed with the mean and the variance given. So if you find the mean difference between two mu and sigma square x1 minus x2 is given here. So when you take square root of sigma square, you will find the sigma. That is square root of this term in the denominator. X1 bar minus x2 bar. This is in the same format, x minus mu over sigma. X is replaced by the difference of the sample means. Mu is replaced by the difference of the population means, mu1 and mu2, isn't it? This sigma has been replaced by sigma square for x1 minus x2. This is sigma square for x1 bar minus x2. Right. So you have all this information substituted in the formula, and then you will convert the two sample into Z transformation, one Z variable, and use normal table to find the probability. Fine. Exercises. You should have a normal table with you hereafter, isn't it? Again and again, I will not open normal table. You should have, because we have seen enough number of problems to use normal table. In a certain machine, if a certain machine makes electrical resistors having a mean resistance of 40 ohms, so mean, population mean, or sample mean, we don't have a sample here, it is population mean, no? 40 ohms. and the standard deviation is sigma 2 ohms. What is the probability that a random sample of 36 of these resistors, no sample you take, the sample size is n, small n is 36, only one sample, isn't it? The concept of one sample. Will have a combined resistance of more than 1458 ohms, then what is average resistance? See, you are going to find the probability of the random variable. Random variable. What is the random variable here? That's what we are going to check. Sample size is 36. The total resistance of all the 36 resistors is equal to 1458. Therefore, what does the sample mean? Total resistance 1458 divided by 36. Isn't it? It is 40.5. So the question is, probability of the random variable x bar, samples mean is your random variable, is more than 40.5 as an average. So the question is, probability of the random variable mean, which is greater than 40.5, that is it. If you convert x bar into z, you are done. The right side of z you have to find, isn't it? So find z. The formula for z is x bar minus mu over sigma of by root n. What is x bar? It is 40.5. What is mu? Minus 40 divided by sigma by root. Sigma is 2, root of n is 6. So it is 2 over 6. 2 over 6. Use your calculator. You will find it is 1.5. Now z value is 1.5 if x bar is 40. If the x bar is 40. So x bar greater than 40 will be equivalent to probability of z greater than 40.5. But we find the area to the left side of the z from the table, isn't it? So this, if you want an area greater than z, what you got to write? Subtract the area left side of z. Now from the table you will find this area, the area to the left side of z is 40.5 is 0.9332. So the answer is 0.0668. This is the probability. So when they ask in probability, we stop here. If they ask in percentage, we multiply 100. If you want the number of resistors as an answer, multiply the probability with the total number of resistors in the population. That's it. The answer is given. A soft drink machine is regulated so that the amount of drink dispensed averages 240 milliliters with a standard deviation of 15 milliliters, isn't it? So average average of the population is 240 ml, and standard deviation of this population sigma is 15 ml. Periodically the machine is checked by taking a sample of 40 drinks. Okay, the sample size n is 40. Sample of 40 drinks and computing the average content. Again, we have to find the average of the sample. So the sample size is n. What is the average of the sample size? X bar. We will check. And if the mean of the 40 drinks, if the sample mean is so value within the interval, if the sample mean is falling within this interval. See, this is mu x bar, mu of the population sigma with respect to x bar. Sigma x bar is not sigma, which is standard error, isn't it? Standard deviation, standard error with respect for this mean. So what we are going to do, calculate this time, mu plus or minus 2 sigma x bar. The machine is thought to be operating satisfied. So if you find the average of the sample and the average falls in this interval, then you say the machine is working good. Otherwise, some adjustments are necessary, isn't it? The company official found that the mean of 40 drinks to be X bar is 2. So X bar is 236 milliliter. Now we found mean. Now the question is whether this X bar is falling in this interval. If it falls, then it is working good. Otherwise, we need adjustments. Fine. Mu x bar. What do you mean by mu x bar? Standard. Mean population mean with respect to the sample is same population mean mu, which is 240. Okay. But sigma x bar is not sigma. Sigma x bar is sigma over root n. Standard error you can call it, or standard deviation with respect to x bar, right? Therefore, sigma is 15 and square root of 40 sample size. It will give you the value 2.372. Now this is your sigma x bar. Mu x bar is here. So from the mean, 2 units of the sigma x bar plus and minus, you are getting an interval. So what we are doing here is mu x bar plus 2 times sigma x bar. Mu x bar is 240 plus 2 times sigma x bar is 2.372. Multiply these two and add with the 240, you'll get 244.743. This is your upper limit. Actually, this kind of estimation is called interval estimation. We will study it later. Next, actually we are forming an interval. Mu x bar minus 2 times sigma x bar is equal to 240 minus 2 times 2.372, which is 235.257. So this is your lower limit, 235.2. 244.7 is upper limit. Do you believe that this sample mean is falling in the interval? Check. Yes, 236 is obviously greater than 235 and lesser than 244. So this sample is falling in the interval. This sample is falling in this interval. Therefore, your machine is working satisfactorily. No adjustments are necessary. That's the conclusion. Okay? This is interval estimation. We estimate the sample, sample mean, whether it is falling in this interval or not. Okay, that's the end of this problem. Next, yes. The random variable x representing the number of cherries in cherry puff has the following probability distribution. So x representing the number of cherries, and the probability. What is the probability that a cherry puff will have 4 number of cherries? Is 0.2. 5 number of cherries, 0.4. 6 number of cherries, 0.3. 7 number of cherries, 0.1. Isn't it? This way. Now find the mean and the variance of mean mu and variance sigma square of x. For this x, we know when there is a probability distribution, what is the formula for mean? Mean mu. mean mu for any probability distribution is expectation of x, isn't it? Which is summation x times probability x. That is, multiply these two and multiply the x value and its probability and then sum them up, isn't it? So we start with 4 times 0.2 plus 5 times 0.4 plus 6 times 0.3 plus 7 times 0.1. Use calculator, and the mean is 5.3. Note down, this is your mu, and of course mu x bar as well. Mu and mu x bar are same. Now sigma x square x bar square is variance. First find the sigma square variance for them, then we will find sigma x bar square separately. Okay, what is the formula for variance? Variance of x, which is sigma square, is expectation of x square minus expectation of x whole square, isn't it? Expectation of x we know, this one is mean 5.3 square. What is e of x square? We will find e of x square. The formula for e of x square is summation x square p of x. This should be multiplied here. That is, square the x value, multiply with its probability, then sum them up. So this should be done for all the probabilities. So first one is 4 square is 16 times 0.2. 5 square is 25 times 0.4. 6 square is 36 times 0.3. 7 square is 49 times 0.1. When you multiply and add all these things, you will end up with 28.9. This is expectation of x square. Now find the variance. Find the variance here. 28.9 minus 5.3 whole square. Use calculator. The variance is 0.81. So here the question is find the variance and mu. That has been done. Remember the variance sigma square is 0.81. The mean of x is 5.3. We want these two information to proceed for point B. Now we take a new sample x bar. We take and find its a sample mean x bar for a random sample of 36 cherry puffs. So the new n, we are getting new information. The sample size is here 36. So we want to find mu x bar. Mu x bar is same mu, which is 5. But sigma square x bar is not sigma square. This is sigma square over n. That is, we know sigma x bar is sigma over root n. So square it on both sides. You will get this sigma square over n, isn't it? Okay, what is sigma square? Variance is 0.81 divided by 36. You will end up with 0.0225. Therefore, this is variance with respect to the mean x bar. Therefore, standard error or standard deviation for the x bar is square root of 0.0225, which is 0.15. This is another result. Do we need them? Maybe for the finding probability next step. Probability that average number of cherries in 36 cherry puffs will be less than, so x bar is the average number of cherries in 36 cherry puffs. So we will go for problem number 3. See, we know it's given here the mean x bar for random sample of 36 series of, isn't it? So probability of x bar less than 5.5, isn't it? So immediately find z. Z is x bar minus mu x bar, actually you should have mu x bar and sigma x bar, isn't it? X bar is 5.5 minus mu is 5.3 and sigma x bar we have found 0.15. This will give you z value is 1.33. Therefore, if x bar is less than 1 point, that is 5.5, which is equivalent to probability of z less than 1.33. Okay. So straight away from the table of normal curve, you will find, because it is left side. The table always shows the area left side of the z value 0.9082 directly from the normal curve. That is the end of this problem. Problem number 4. The amount of time that a drive-through bank, I think a drive-through bank teller spends on a customer is a random variable, which is a continuous random variable with mean 3.2 minutes and the standard deviation sigma is equal to 1.6 minutes. Compared to this mean, the sigma is 2 minutes. For random sample of 64 customers is observed, sample has been taken as 64, the size n is 64 now. Find the probability that their mean time at the teller's window is service time. Okay? Mean service time. Yes. So there are three cases. Obviously, what is x bar here? X bar is the mean service time. Mean service time, you can say. And what is mu? Mu or mu x bar, both are the same, so 3.2. Sigma is 1.6, n is 64, n is 64. So you will find sigma x bar, which is 1.6 over 64, root of 64, root n, sigma by root n, which is 8. 1.6 divided by 8, 0.2. This is standard error or standard deviation with respect to x bar. Now let's come to the point. What is the question? Probability. The probability that their mean service time is at most 22.7, at most maximum. So problem A suggests the probability of x should be lesser than 2.7. At most maximum value is 2.7. X bar falls lesser than 2.7. What is this? So immediately we need z value. What is z? Z is x bar minus mu x bar over sigma x bar, isn't it? X bar is what is the sample mean? Sample mean, that is x bar is given here 2.7. So 2.7 minus mu x bar is 3.2 over 0.2 is sigma x bar found here. The answer is z is negative 2.5. If x bar is less than 2.7, it is equivalent to probability of z less than negative 2.5. Straight from the table. isn't it? Straight from the table, which is when z is less than some number, it is straight from the table. 0.0062 is the answer for case 1. Next, more than 3.5. More than 3.5 minutes. Okay, you should remember this information mean. Just I will erase some part. So we are addressing part B. Probability of the mean should be more than 3.5. Obviously, which is there should be some z value. Z is x bar is x bar. The formula you write x bar is 3.5. Mean is 3.2 divided by 0.2. The answer is 1.5. 1.5 positive. So when x bar is greater than 3.5, which will be equivalent to probability of z is greater than 1.5. When you want the area right side of z, you will write 1 minus probability of z less than 1.5, which is 1 minus this one can be found from the table, which is 0.9332, isn't it? Go to the left extreme column 1.5 and the right side will be 0.09332. Check it. When you subtract, the answer is 0.0668. Now, question number C. If you have any question, you can certainly interrupt me. Okay, let us address 3. It must be between two values, isn't it? So C, at least, so minimum is 3.2 and less than maximum 3.4. So x bar, the mean lies between these 2 points, 3.2 less than x bar less than 3.4. This is what. So we want two different z values. Z1 for upper value 3.4. We will find 3.4 minus mean is 3.2 over 0.2, which is 0.2 over 0.2, which is 1. And Z2 for this value 3.2 minus mu is also 3 point, so it will be 0. Between 0 and 1, isn't it? Then Z lies between 0 and 1. So yeah, upper limit is 1, lower limit is 0. So this can be addressed in the normal curve. This is the normal curve. This is 0, mu is 0, this is, and you want the area between this one. So find the area up to 1 and subtract the area in the first half. First half area is 0.5. So we will write this one as probability of z less than 1 minus probability of z less than 0. And this one should be found from the table, which is 0.9413. Go to 1.000. You'll find. 0.9143. And if is that less than 0 is the first half, the total area is 0.5. So try 0.5. The answer is 0.3413. That will be the end of this problem. Now we start the next chapter, sampling distribution of S square. I suggest we will start this chapter in the next class. Okay. What do you think? Or shall we continue? Only few problems. The chi-square distribution, the T distribution we will discuss. Okay. Let us continue. The sample distribution of the variance. If S square is the variance of a random sample of size n taken from a normal population having the variance sigma square, then the statistic, see, chi-square, this notation stands for chi-square distribution, a new distribution we are going to see this chi-square distribution with degrees of freedom. For data set, there will be degrees of freedom. Here it is V is n minus 1, denoted by small v, which is n minus 1, sample size minus 1, right? We need this information to check the data value, the x square value in this table. Now, what is this? We have seen the formula of variance. The same, you can write expectation of x square minus expectation of x whole square, isn't it? In other words, it is called xi minus c. If you have data, how do you find variance? Data set directly without a probability. You will find x minus x bar. We will find this average of all the data. Isn't it? If you have 5 data, 2, 3, 4, 5, 6, and if you believe 4 is the average, this is x, this is x bar. From every x, you will subtract x bar. So 2 minus 4 minus 2 minus 1. So, and then you will square it. Sum them up. Divide by n. Divide by n minus 1 here. That will be your variance. So variance divided by this variance is sample variance. This variance is population variance. Okay? That is it. So this is analyzing the variances, not ANOVA actually. We are finding the probability distribution of variances, which is approximated by chi-square distribution. So this theorem allows us to use the sample variance to make inferences about the variance of the population, isn't it? We have to conclude something about the population variance by using the sample variance. This formula will be used to find chi-square values. Now, not an exercise problem, another information. The probability that a random sample produces a chi-square value greater than some specified value is equal to the area under the curve to the right of its value. In normal curve, we have seen the area to the left of the z value, isn't it? But here we are going to find chi-square value to the right side of the value. Chi-square value. Area to the right side, isn't it? Right side of chi-square value. Okay, let's see here. To the right side. Now, it is customary to let chi-square alpha represent chi-square value above which we find an area alpha. See, what do you mean by chi-square alpha here? This value on this axis is chi-square value. Alpha says that the area right side of this is alpha. Isn't it? And remember, this curve is not symmetric. So you cannot simply subtract one on this. But you see, we can find this from positive 0 to infinity chi-square because it's square values. It's not symmetric about mean or something. Table A5 from the textbook gives the values of chi-square alpha for various values of alpha and b. Gives degrees of freedom. The areas alpha are the column headings. The degrees of freedom V are given in the left column. What is it? Let me show you a chi-square table first. This is a chi-square table. See, degrees of freedom given in the first column, and the titles are the alpha values. So what you find inside the table is the chi-square value. So critical values of chi-square distribution. Critical values, table value. There are two values. One is calculated value, another one is critical value. So the critical values are given here for chi-square, but the area will appear on the top row, first row. And the degrees of freedom will be in the first column. So we have to find first the degrees of freedom. The row should be chosen with respect to the degrees of freedom, and then go to the appropriate area column. Then find the most fitting chi-square value from this table. We will do it slowly. Let's go back and check what is going on here. The table A.5 gives values of chi-square. Okay. Hence, the chi-square value with 7 degrees of freedom. Note it down. Degrees of freedom is 7. Leaving area to the right is alpha is 0.05. So degrees of freedom V is 7, alpha is 0.05. So the chi-square value is 14.067. We have to check it from the table. Okay. Go and show you. Degrees of freedom is 7. You are here. Move this way. Alpha is 0.05. Is there 0.05 here? No. In this table it's missing. So go to the second table. Only 2 tables. Again, degrees of freedom is 7. In this row you are going to browse 0.05. This is your alpha. The area to the right side of chi-square value. So in this column and this row meets at this point. 14.067. You're right. No, the answer given on the table is right. 14.067. Given is right, isn't it? Owing to lack of symmetry, we must also use tables to find. It's not 1 minus alpha. It's actually we cannot subtract the value of x, isn't it? If you want chi-square value for 0.95, you have to separately find what is 0.95. What if alpha is 0. If alpha is 0.05, then 1 minus alpha will be 0.95. Isn't it? But there is no symmetry, so we should separately find it for v equal to 7. The answer is 2.167. You can verify with the table. Okay. Now t distribution. It was assumed that the population standard deviation is known for the previous section because we were analyzing the variance. This assumption may not be reasonable. It's unreasonable in situations where the engineer is quite familiar with the system or process. However, in many experimental scenarios, knowledge of sigma is certainly no more reasonable than the knowledge of the population mean. So most of the time, you may not end with the standard deviation. So if x bar is the mean of a random sample, you take a small sample of size n and find its mean sigma bar, x bar from a normally distributed population. The population mean is mu and variance is sigma square. Then the random variable, actually, population variance is sigma square. We may not have the idea of sigma square. We have S. We have sample standard deviation. S square is sample variance. So S is sample standard deviation. So we have S over root n. So in this, the formula of z, which is x bar minus mu x bar over sigma x bar, isn't it? The sigma x bar can be found by using S over root n when population standard deviation is not known. We can find sample standard deviation and then using the same formula, it will be called actually Student's t distribution. As a t distribution with n minus 1 degrees of freedom. N is sample size, so the degrees of freedom will be n minus 1. What do you mean by the degrees of freedom in physical form? I will let you discuss. But if you understand it's okay, otherwise ask this question in the discussion session. Okay. Fine, here this is t distribution. The formula is very similar to Z, but instead of sigma we have sample standard deviation. That is it. So the concept here, we are assuming that we have a small sample. We don't have an idea about the population standard deviation. Now, in another corollary of this theorem, there are n independent random variables x1, x2, xn, the independent random variables that are all normally distributed with the mean mu and standard deviation sigma. Mean of every there are different n samples, maybe from same population or not very with the standard. All are normal with the same mean and the same standard deviation, so they are from same population. Let x bar the mean of all random variables. X bar is mean of all, so sum them up and divide by n. That is it, x bar. And the same formula of variance, xi minus x bar whole square divided by n minus 1. The formula that we have used in the first chapter. So variance. This is sample mean, this is sample variance. Okay. Then the random variable t. This is for n samples, n random variables, and different random variables. Then summation of all the average of all the random variables x bar, the variance of them is s square. Then the random variable t has a t distribution, small t with the degrees of freedom is n minus 1. So that's the theorem, the corollary. The distribution of t is similar to the distribution of z in that they are both symmetric about a mean of 0. T distribution, you can see the figure on the next slide, will be looking like a normal distribution. Both distributions are bell-shaped, but the t distribution is more variable owing to the fact that t values depend on the fluctuations of two quantities, x bar and s square, sample mean and sample variance. whereas Z value depend only on changes in X bar from sample to sample. The distribution of T differs from that of Z in that the variance of T depends on the sample size n and is always greater than 1. So only when the sample size n is approaching infinity, both distributions will be meeting. They will be same. When for sample size is larger, which is approaching infinity, the T distribution becomes Z distribution. A normal distribution, Z is for normal distribution. So the graphs of the relationship between a standard and normal distribution, V when degrees of freedom is infinity, this one is normal distribution. And T distributions with two different degrees of freedom. V is 2, V is 5. So what is second graph? What is the meaning of second graph? Symmetry property about 0 of the T distribution. See, when T alpha, if you find a T value for a given alpha, this it means that the area is lying in the right side, just like chi-square distribution. Area lies in the right side, not like the table of normal curve. Isn't it? In the Z curve, you are finding the area to the left side of the Z value from the table. But here in the table, it's given the area to the right of the T value. So if I give you negative T alpha, it means you are here. The area to the left of T. The area to the left of T, which is equivalent to T 1 minus alpha. So if alpha is 5 percentage, we can write 0.05. 1 minus alpha is 0.95. So this is this if alpha is 5 percentage. If alpha is 0.05, then 1 minus alpha is 0.95. So this is T95. T 0.95. What does it mean? The T value to the right of the T value, the area is 95 percentage, 0.9. So left side there will be only 0.05 area alpha, isn't it? Clear? For T alpha, if I write T 0.05, it means the right side of the area is 0.05. Right side of T. T value can be found from the table. It is customary to let T alpha represent the T value above which we find an area equal to alpha. We'll go to the table, T table. T value with the 10 degrees of freedom. What is it? 10 degrees of freedom. V is 10. V is 10 and the alpha to the right side of T we need area 0.025. Then what is T value? From table A4. Okay. From table A4. Okay. Degrees of freedom is 10. Here we go. The 10 is here. Alpha is 0.025. Do we have 0.25 here? No. Move to the next. Again, degrees of freedom is 10. Go through this row. 0.025 is here. The area to the right side of T value is 0. Now the area is on the top. T value will be found here. T value is 20. 0.483. Is it? Yes, 10. Degrees of freedom is 10. The area right side is 0.025. So the answer is 20.483. T distribution is right. This is T distribution, yes. I have checked the wrong again. T distribution, degrees of freedom. T is degrees of freedom 10, and the alpha is 0. We have wrongly checked with the chi-square table. That's it. Now this is T table 0.025. Go here is 2.228. So 228. This one. This one. So that's it. It's right now. 2.228. Since the T distribution is symmetric about the mean of 0, we have T 1 minus alpha is equal to minus T alpha, which means that if you are looking for 95% area in the right side, the T value for which 95% area in the right side, which is equal to negative T value for alpha, for which 0.05 area is in the left side. So negative sign says that the area alpha is the left side. So whenever T comes with negative value, it says that the area, the alpha is in the left side. Okay. Therefore, the right side area will be 1 minus. That is the T value leaving an area of 1 minus alpha to the right, and therefore area alpha to the left is equal to the negative T value that leaves an area alpha to the right tail of the distribution. That is what we have seen that. Now, an example has been given here. The same what we have discussed. T.099 is equal to negative T.01. So 0.01 area to the left of T value. Therefore, 99% area to the right. Some graph. This is T distribution table. T second table for T distribution is chi-square first table, chi-square second table. Let us start exercise problems. Okay, we got to find all these things from the table. Note down all these things, and we will go to chi-square table and find chi-square 0.025, chi-square at alpha 0.01, chi-square for alpha 0.05. 3 chi-square values for 3 degrees of freedom. We'll stop with this problem. The T distribution problem will be discussed in the next class. Okay. Almost times coming up. You need to be ready for the next exam as well. So note down chi-square 0.05, alpha value 0.025, and degrees of freedom is 15. Now, for all the 3 terms, we will find an answer from chi-square distribution. So find alpha. Now, first I am finding the value for chi-square 0.025 when degrees of freedom V is 15. This is my alpha value. Do we have alpha on the top? No. Go to the next table. What is chi-square 0.025? This is alpha value. V is 15. So go to the degrees of freedom. V is 15 in this row. Alpha is 0.025. This is alpha. You will meet here 27.488. First answer is 27.488. Next, chi-square at 0.01 when v is 7. Alpha is 0.01. Do we find it? Yeah, 0.01 here. Degrees of freedom v is here 7. So they will meet here 18.475. Next, third one is chi-square 0.05 when v is 24. V is this one, 24. 0.05 do we have here? Yeah, just here. This is alpha. So when they meet 24, 36.415. That is it. Three answers. First one is 27.488. Next 18.475. 36.415. The third one. That's the end of chi-square distribution. We have only one problem to discuss. Chi-square. All the answers are here. Now, the similar way you should work with the T distribution. We will solve the T distribution in the next class. Thank you very much.